a capacitor consisting of the two circular conducting plates here, with the radius equal to the capital R and the separation between the two plates just equal to the L. So this capacitor is connected to the sinusoidal AC source of the amplitude equal to the V0 here and the angular frequency equal to the omega. Okay. So now we just want to show that the maximum electric energy stored in the capacitor is equal to this expression. So one thing, let's consider the mechanism of this structure first. So now you can see that we have the AC source here, right? It means that the current will just flow in back and forth respectively. Okay. And then it means that the electric field will just point to this direction, and sometimes later we just point to this direction, and then to the opposite direction, and etc. Then it means that we can just compute the electrical potential energy stored inside this capacitor, okay, because we have the electric field inside this structure. Then we can compute the electrical potential energy stored inside this capacitor. So then let's just start from the equation. We say that U, right, the electrical potential energy UE from the chapter of the conductor, from the chapter of the capacitor, right? We said that the UE equal to the 1/2 and then the C and then the V0 square, okay, because right now we just want to find the maximum energy stored inside this capacitor, so that's why we need to use the V0, the voltage amplitude of the AC source here, and then this C is going to be the capacitance of this capacitor. So what is the C, right? By definition, okay, we said that from the parallel capacitor we have the C equal to the epsilon naught times the A and then over the L, where the A here is going to be the surface area of each plate, right? And the L is going to be the separation between the two plates here. So then we get that equal to the epsilon naught and then the pi capital R square and then over the L, okay, because the area of each plate just the pi R square. So now we just plug in this C into this equation. One get that the UE, right, it's going to be equal to the 1/2. So now for the C, it's just the epsilon naught pi R square over L and then times the V0 square. Okay, so that's the same as this expression. So this is the answers. So now for the part B. For the part B here, we just want to find the maximum magnetic potential energy stored inside this capacitor. Okay, we just want to find the maximum magnetic potential energy stored inside this capacitor. But then how should we start, right? How should we start? Because I mean, so far we don't have any equation that can be used to describe the magnetic potential energy of the capacitor. We have only the magnetic energy density, okay, we have only the magnetic energy density. So let's look at this idea. The idea is just simple. So we say that we just want to find the magnetic potential energy, right, the UB, okay. So the idea is that first of all, let's find the magnetic the magnetic energy density first, okay. So the difference between these two is this going to be the capital U and this going to be the small u. Don't forget that the small u just for the energy density and the capital U just for the potential energy, okay. So we need to find the UB first, the magnetic energy density. But then how can we find the UB, right? We can find the UB from the magnetic field. Okay, we can find the UB from the magnetic field. But then what is this magnetic field? Okay, so we have learned from the Maxwell Ampere's law, right? So we said that if we have electric field in this region, and now this electric field is not constant, okay, it just point in this direction and then to the opposite direction and then to this direction. So you can see that this electric field is not constant. It means that the electric flux, right, electric flux through just the virtual area here is not constant as well. So then we can have the induced magnetic field inside this regime, right, just come from the displacement current. Okay, so that's be the way that we can find the this induced magnetic field. So then to get the induced magnetic field, then we need to know the displacement current first, right? We need to know the displacement current first. Okay, so that's be how so this will be how we should start, right? We should start by finding the displacement current first, and then use the Ampere's Maxwell law to find the induced magnetic field, and then use these results to compute for the magnetic energy density, and then finally to get the magnetic potential energy. Okay. What is the displacement current? We said that the displacement current, right, is going to be equal to, okay, so let's look back. The displacement current is equal to the epsilon naught and the flux E by dt. Okay, epsilon naught, and then the d flux E by dt. So what is the flux E, right? So let me just the flux E is going to be the amount of the electric field, lines, right, passing through this virtual area. Okay, so let me just assume that the virtual area is here. And then this area we have the radius equal to, let's say, the small r, right? Let's say the small r here. And now this electric field just passing through this area. Okay, so then we can get that the electric flux, right, passing through the area here is going to be equal to the flux E, okay, equal to the electric field E, and then times the area, right? The area just the pi small r and then square. Okay, so this area we did just equal to the r, so we have the pi small r and then square, and the electric field E, right, is going to be equal to, okay, because we just want to have the maximum magnetic energy stored inside this capacitor, right? So now I'm going to use the voltage amplitude to solve for this one. So now this E, right, is going to be equal to the, no, wait, sorry, I cannot do that because we need to take derivative of the terms first. So we can get equal to delta V, okay, and then over the L, right? So where the L here, it just be the separation between the two plates, okay, or just equal to the V naught over the L, and then times the sine of the omega t. So then we can get that the electric flux, right, is going to be equal to the V naught over the L, and then times the pi r square, and then times the sine of the omega t here. So now we can just plug in this electric flux into this equation. So we have that, let me add one more page. Then we have that the ID, okay, equal to, so these terms are constant, right? So we can just bring it out from this differentiation. So it's equal to the epsilon naught, the v naught pi r square, and then over the L, and the d by dt of the psi omega t, okay, which is equal to, okay, so let's take derivative of the psi, right? So it's just equal to the cosine omega t, and then we have the extra omega as well. So we have the epsilon naught, the v naught, the omega, the pi r square, and then over the L, and then times the cosine omega t, and that's it. Okay. Now let's use the Ampere's Maxwell law to solve for the induced magnetic field. Okay. So now from the Ampere Maxwell law. Okay, so it said that the closed loop integral of the B dot dl, right, equal to the mu naught and then times the enclosed current and then plus the displacement current. So now in this regime, right, we don't have any wire, so it means that we don't have any the real or the physical current here. So the I enclosed just equal to the 0. Now for the ID, right, we have it already equal to this one. Then on the left hand side, right, you can see that the magnetic field, right, this magnetic field here, if you just circulate about this circle, okay, about these circles, so we have that the B and then times the circumference of, the ring, right, just of the circle, 2 pi times the R equal to the mu naught and then times the ID. The ID is here. Okay, the ID is here. Or I can get that the magnetic field, right, when the R is less than the capital R. Okay, so don't forget that right now we just considering the magnetic field which is inside this region here. Okay, but the R is less than the capital R, is going to be equal to, so the pi just cancel out. Okay, so 1R just cancel out. And now I have the epsilon naught times the mu naught, which is equal to the 1 over c square. Okay, remember? So then we get that is equal to the v naught still here, the omega still here, and the 1r still here. And then over we have the 2 here, right? 2 times the L and then times the c square. Okay, because the 1 over c square equal to epsilon naught and then times the mu naught here, and then times the cosine omega t. Okay, now so let's find, okay, so now we got this step already. So now let's find the magnetic energy density. Okay, so let's find the magnetic energy density. Let me change the colors. Okay, UB, right, equal to the B square and then over the 2 times the mu naught, right? One thing, this UB is not the average value. Okay, so it still depends on the times t, because right now this magnetic field just depends on the time, so it means that this UB depends on the time as well. so it's just equal to, okay, so let's plug in this B into this equation. Okay, so we're gonna have 1 over the 2 times the mu naught and then B square, right, which is the V naught the omega times the R, and then over the 2L and the C square and totally square here. Okay, and then cosine square omega t. Okay, so this will be the magnetic energy density. Now next, okay, so now we have the magnetic energy density already, so now we can find the magnetic potential energy, the capital U sub B. Okay, so let's find the magnetic potential energy U sub B, right, is gonna be equal to the integral of the UB and then D of the volume, right, because we say that the UB here, right, the energy density equal to the energy over the volume, so it means that the magnetic potential energy equal to the integral of the energy density and then times the volume. Okay, next let's just plug in the this UB into the equation. Okay, but right now you can see that this R is not constant anymore, right, because the question is we just want to find the magnetic potential energy stored inside this capacitor, but right now we're just looking only for the small ring which the radius equal to the R. So it means that we need to make the integral from the 0 and then to the capital R, right, to cover all the things here. Okay, but then first of all, what is the D volume here? Okay, the D volume is going to be the volume of this hollow cylinder. Okay, it's going to be the volume of this hollow cylinder. So let me just write down as this one. Oops, sorry. Okay, so let's say that the length of this cylinder, right, is just equal to the L. Okay, and now the radius of this cylinder equal to the small r. Okay, so wait. Yep, kind of something like this, right? And then the okay, so we have the small r here. We have the small r here, and then the thickness of this cylinder, okay, equal to the dr. Let's say the dr. So it means that in this picture, right, the magnetic field is gonna circulating. On this hollow cylinder. Okay, but if you just look here, it's be the ring, right, compared to this one. So now the electric field just passing through this region here. Okay, so now from this picture, right, we can get that. Okay, from this picture we can get that the D okay, the D volume, okay, is going to be equal to what? Equal to this surface, right? And then times the length of the cylinder. So the surface area here is just equal to the 2 pi r and then times the dr. Okay, so we have seen this many times already. And then times the length of the cylinder, just equal to the L. So then it's going to be equal to the 2 pi L and then times the R dr here. Okay, so now let's just plug in this one into this equation and also for the UB here as well, right? So then we get that UB, okay, equal to 1 over the 2 times the mu naught, and then the V naught omega over the 2 times the L and the C square, right? And then square here, and then times the cosine square omega t. So this R square is not constant, right? So it's going to be inside this integration. Okay, so now we have the 2 pi L here. Let's just multiply together, 2 pi L, and then, right, the integral of, okay, so now we have this r, but square is going to be the r square, and then multiply with this r, right? It's going to be the r cubed dr, and then make the integration from the 0 to the capital R, because the question needs to find the magnetic potential energy stored inside this capacitor, right? So this capacitor will be limited to the radius equal to the capital R. So we just ignore the outside here. Okay. Then after the integration, right, and then we just rearrange, then finally we can get that. Okay, so let me just keep the simplification part. Okay, we can get that. Okay, let me copy this. The UB, right, is going to be equal to this one. Okay, just check by yourself. Okay, so please check this by yourself. Now for the part C. Okay, so now we just want to approximate the ratio of the UB over the UE numerically. Okay, so then before we working on this one, let's guess first. So what do you think? Which one will have the higher numbers between the UB and UE? Okay, so let's take time to think. I think maybe you can guess, right? I think you can guess that the UE should be greater than the UB. Why I say that? Because I mean the objective of this capacitor, right, is just to generate the electric field, not the magnetic field. So then we can guess that the energy due to this electric field part, right, should be greater than the energy due to the induced magnetic field part here. Okay, but now let's just find the number. So okay, we have the UB and then over the UE, right? So we just bring this one divided by this one. Okay, but I'm gonna skip this part because it's just easy, so you can just do the algebra by yourself, right? So when you have the UB from the part B divided by the UE from the part A, so then after rearrange the equation, you will get that equal to the 1 over the 8, okay, and the omega times the R and then times the C and then square. Okay, so now let's do some approximation. let's do some approximation. Let's say that, okay, so if we have the frequency of, the AC source, right, in Thailand equal to the 50 Hertz. Okay, so if the frequency here equal to the 50 Hertz, so then you can compute for the omega. And now for the R, right, the radius of this capacitor. Okay, so normally let's say that if you have the radius about the 1 centimeter, okay, about 1 centimeter, so if you just plug in this number, right, into the equation, and also with the speed of the light in the vacuum, then you can approximate that the UB over the UE should be about 10 to the negative 17. Okay, so it means what? It means that the UE is much greater than the UB, right? It's just making sense. Okay, it means that the magnetic field created, induced inside this capacitor, right? So it's going to be contribute very details compared to the electric field which is created inside this capacitor.